Okay, welcome back. Let's look at now something somewhat different, matrices. Okay, so vectors are examples of matrices of certain dimensions. So far we've added vectors together and multiplied vectors by scalars. We're going to do the same stuff to matrices, add them together and multiply them by scalars. And we're also going to multiply matrices together. Title of the section 1.3 is Matrices and their Algebra. So we'll define a matrix. We'll give a way to add matrices together of appropriate sizes. We'll give a way to multiply matrices together of appropriate sizes. And we'll also multiply matrices by scalars. And we'll give some properties of that resulting addition and multiplication. Might point out, this is something we didn't do with vectors. We never took two vectors and multiplied them together and got another vector. We did have the dot product where we took two vectors and dotted them together and got we got a scalar out. Dot product is also called scalar product. So this is something fundamentally new and will be defined, it turns out, in terms of dot products of certain vectors. Okay, so first a definition, granted a somewhat informal definition. Matrix is a rectangular array of numbers. An m by n matrix is a matrix with m rows and n columns. First dimension counts the number of rows, first row, second row through nth row. Second dimension counts the columns, first column, second column through mth column. And we'll take quite often capital letters to represent matrices. Here's matrix A. We'll denote its entries with a corresponding lowercase letter, lowercase a. And we'll put double subscripts on those entries to indicate where they occur in the array, in the matrix. So A sub ij occurs in the ith row in the jth column. For example, A sub 2, 1 occurs in the second row in the first column. A sub 1, 2 occurs in the first row in the second column. Probably about half the time we deal with matrices, we'll deal with square matrices in which m and n are the same size. But we'll deal plenty of times with matrices that aren't square. Okay, Fraley and Beauregard decided to define a matrix product first. Actually, matrix sums are pretty easy to deal with. Matrix products are defined in a kind of awkward way for reasons to be elaborated on probably in the next several chapters of material. This is a very fundamental thing that we'll do, this idea of a matrix product. And it involves some dot products itself. All right, so what we're going to do is look at some of the rows and columns of the vector, of the matrices in the product, and take dot products of corresponding rows and columns of these matrices. More precisely, much more precisely, hopefully, if we take matrix A with entries, lowercase a sub ik, let this be an m by n matrix, and let matrix B with entries b sub kj be an n by s matrix, then, well, just a second here. So let's see, the second dimension of matrix A, that would be the number of columns of matrix A, has to be the same as the first dimension of matrix B. That's the number of rows in matrix B. So these two parameters, these two dimensions, have to be the same in the following definition, and you'll see why when we state the definition. Then the matrix product, matrix A times matrix B, is the m by s matrix, let's call it C, with entries c sub ij, where c sub ij is the dot product of the ith row vector of A and the jth column vector of B. That is, c sub ij will be a sum from k equals 1 to n of a sub ik times b sub kj. All right, let's make sense out of that. And we've got a picture on the next page to elaborate on it as well. First off, the dimension of the product is the first dimension of the first element of the product and the second dimension of the second element in the product. So m by n matrix times n by s matrix yields m by s matrix. That common dimension of n doesn't play an obvious role in the product. It doesn't play any role in the size of the product. Matrix AB, matrix C equals AB is how we'll deal with this, and introduce additional characters probably when we do computations with these and when we prove theorems about them. This is potentially quite messy stuff, so we'll try to be a little careful with notation. Now, they say we're going to take the ith row vector of A. Okay, if we look at a row vector like this one, how many entries does this row vector have? As I should say, how many components, if we're treating it as a vector. So how many components does this, say, second row vector have? It's got n of them, the number of columns. In fact, the number of columns tells you the number of entries in a row vector of matrix A. That was the second dimension. We're going to take that row vector of A and take a dot product of it with the jth column of a vector of B. So if I were to look, as we will on the next page, at a column vector, so it won't let me highlight just columns. Try something else. No, it won't let me highlight just columns. If I were to look at a column vector in matrix B, I need the number of entries of that to equal the number of entries we had in that row vector of A. Row vector had n entries. We'll need the column vector of matrix B to also have n entries, n components. The number of entries or number of components in a column vector of a matrix is the number of rows of the matrix. I'm bouncing around between rows and columns. How many rows does matrix B have? N. Okay, so the column vectors of B have n entries and the row vectors of A have n entries. Those are the same. The dot product exists. I mean, I can't take a dot product of a vector from R3 with a vector from R5. I run out of entries in the first one before I run out of entries in the second one. I got to have those dimensions the same. And that's the reason you need the n here in the second dimension of A to be the same as the n here, the first dimension of B. Okay, it's a little clunky, but we'll do so many of these, it'll become second nature to you. Here's a picture out of the book in terms of how to take matrix products. Matrix AB, say with the entry C sub ij is given above. Here's matrix A written out in terms of indices as the book doesn't. Here's matrix B written out in terms of the indices, the double subscripts. And if we want to find the ij entry, we'll take of the product, we'll take the ith row of A and dot it with the jth column of B. So that'll be AI1, oh, how about this, first one times first one, plus second times second, up through last times last. You run out of A's the same time you run out of B's? Yeah, there's a n of these A's and there's also n of these B's. That was the dimension constraint. Here it is in terms of a picture. Okay. We'll just illustrate this with some straight up products here shortly, but I want to make a very, very important observation. So it's going to play a huge role in what we do in the future. Note 1.3.a, remember that. So we'll refer to note 1.3.a quite a bit in the future computations. Suppose we take matrix A to be an m by n matrix is given here. And suppose we consider a vector, x vector with entries x1 through x sub n. So it's a column vector in Rn. We could also interpret it as an n by 1 matrix. And we've used the square brackets on these vectors. you notice, we're also using the square bracket notation on the matrices. All right, so if I wanted to take this matrix and multiply it by this vector, well, that'll work. This matrix is n by n. This vector is n by 1. It'll work. In fact, the result should be an m by 1 matrix. So let's see what happens. Okay, so here's matrix A. Here's that column vector x. If we compute that product, we'll do first row times first column. There aren't any other columns, so that's it. Second row, first column. Last row, first column. And that'll produce, when we do the dot product thing, we're interpreting these all as scalars, that'll give us, for example, a11 times x1 plus, a12 times x2 plus, and so forth, up through a sub 1 sub n times x sub n. Add them all together, that produces the first entry. Do that with the second row, first column, produces this. Through the last row, first column, only column, produces this. I predicted we'd get, what was it, an m by 1 matrix. It's certainly by 1. There's only one column. I mean, the entries are complicated with all the additions and stuff, but it really is just one column. And how many rows? You can look at that first index, 1, 2, m. M rows, one column. Told you so. It's m by 1, as predicted. I'm not quite done with that, though. Let's do some more manipulations here. Let's take that m by 1 matrix. If you like, I could consider it a vector in Rn. And we've got all these additions. Let's break this up into a sum of a bunch of vectors. We're going to do it like as follows. I'm trying to get it all on the screen at once, but the fonts get kind of small. Okay, so let's break this up into a sum of a first vector, a second vector, up through an nth vector. All right, we'd have x sub 1 times all of these entries here. We'd have x sub 1 times a11, a21 through a sub m1. We'd have x sub 2 times a12, a22 up through a sub m2 and so forth. So we can take that matrix product and rewrite it as follows. So I'm going back. This is totally a conversation that we could have in either the matrix or the vector setting, but it's totally a conversation that I want to have in the vector setting. So we can write that previous thing as this particular dude. That's a linear combination of these vectors. This is a linear combination of the column vectors of matrix A. And the coefficients are the entries in vector X. In any product of the form matrix A times vector X, we get a linear combination of the columns of matrix A, the column vectors of matrix A, with coefficients as the components of vector X. Columns of matrix A, right, columns of matrix A. These came in as coefficients, first x1 and x2 up through x sub n. First x sub 1 and x sub 2 up through x sub n. So whenever you see an AX, where A is a matrix, X is a vector, what you're getting is a linear combination of the column vectors of that matrix with coefficients in that linear combination given by the components of vector X. All right, so it may be a while before we use that at length, but we're going to use that a bunch. Let's look at an example, a not very complicated example, where we're just going to find, excuse me, section, where are we here? Section 3.1 or 1.3. There we go. Okay. So we were asked to consider two matrices, then take a matrix product. First off, the dimensions have to be correct. Matrix B here is a 2 by 3 matrix. Matrix C is a 3 by 2 matrix. So we can multiply B times C because we've got the same number here as we have here. So we can multiply B times C. We can multiply C times B as well because the second dimension in the product C times B, the second dimension of the first matrix is 2, and the first dimension of the second matrix in the product C times B is also 2. But these ain't going to be the same. B times C can't possibly equal C times B because when we multiply B times C, we can do that because the 3's are the same, but the product will be 2 by 2. B times C will be a 2 by 2 matrix. Similarly, C times B will be a 3 by 3 matrix because of the 3's here in that product. So we can't have B times C equals C times B. They ain't even the same size, so they can't be the same matrix. All right, and that's the reason we're doing this one as an example. Practice on taking matrix products and an observation that we don't have commutativity. So finally, an example of something in which you don't have commutativity. All right, you want the product, then we'll do our thing. Think of it as row dotted with column, because that's what it is. We'll take the first row dotted with the first column. That'll give us 4 times 2 plus 1 times 0 plus -2 times -3, which is exactly this entry here. So here's the first row, first column entry of the product. First row, second column. Do the dot product deal, 4, 1, -2, dotted with -1, 6, 2, produces this. What did I say that was? First row, second column? Yeah, in this first row, second column. So when I take we set it up as the ith row and the jth column, I do that dot product, I get the ij entry down here. Here we've got a, say, second row, first column, that'll go here in the dot product. Second row, second column goes here, having, in this case, 3 for the second dimension of B and 3 for the first dimension of C allowed the dot products to exist. And you can see I'm going to go through this one using rows. That'll produce only 2 rows. Go through this one producing columns. That'll only produce 2 columns. There you go. There's your 2 by 2 product B times C. And when we simplify, not that the numbers mean anything in particular, just practicing taking products, we get this 2 by 2 matrix. So practice these. You just do rows of the first dotted with columns of the second, and you put the results in the right place. Let's try another one. Let's take C times B. Okay, we're going to do row times column. Is this one quicker? Because I've only got 2 things to multiply. Yeah, but I'm going to have to do this, like 9 times? We're going to get a 3 by 3 matrix out. It's exactly the same amount of arithmetic. All right, so we'll do first row, first column. That'd be 2 times 4 plus -1 times 5. 2 times 4 plus -1 times 5. Now, I've written these supplemental notes out in the beginning with all this arithmetic shown so you can get the hang of it. Might ask you, hey, where did this entry come from here? Let's see, this is the third row, second column. So it should be third row of this times second column of that. Should be -3 times 1, 2 times -1. And that's precisely what it is. I can tell from either going into this in terms of a row or a column where it'll appear down here in the product, or I can look down here in the product, see where it is, and reverse engineer and figure out where it came from in terms of rows and columns of first and second matrices in the product respectively. And I do my arithmetic and simplify things a little bit, and we get this. So the big takeaway from this is there it is in computationally and how you, in terms of how you compute matrix products. It's quite straightforward, potentially quite tedious because it's just arithmetic. It's multiplying and adding. Might point out It's not quite too early for this. And if we had a bunch of zeros in those matrices, that sure would streamline all this arithmetic. So if I ever ask you, what's your favorite number in this class, the answer is 0. Because arithmetic with 0 was easy. I've even mentioned that in the past, I think already. By the way, your second favorite number is 1, because arithmetic with 1 is almost as easy as it is with 0. The multiplication is easy with the 1s. And the addition, it ain't too bad either. All right, so the takeaway on this is we did not get B times C to equal C times B. This is not a commutative operation. So I'm going to step out on a limb here and claim this is the first time you've seen a mathematical operation that ain't commutative. If I'm wrong, it's probably because you've seen matrix multiplication before. There's another operation out there that you'll see in your freshman and sophomore experience, and that's cross product of vectors in R3. You'll see that in Calculus 3, and before we're done here, you'll see it in here as well. And that's also an example of something that's not commutative. But the standard example of a non-commutative mathematical operation is matrix multiplication. Those of you that have more algebra ahead of you, like our modern algebra classes, lots of the examples will be motivated by matrices or based on matrices. Yeah, that's because they give you good examples and your most familiar examples of a mathematical operation that isn't commutative. All right, some more definitions, and then we'll actually define what it means to add matrices together. That's way less complicated. The main diagonal of a square matrix, an n by n matrix, so this is something that only applies to square matrices. We're going to do a bunch of things that only apply to square matrices. Multiplication is not one of them, neither is addition, but several of the things we'll do will require that we have square matrices. Talking about a main diagonal is one of them. The main diagonal of an n by n matrix is the entries A11, A22, A sub n. So, hey, here's a matrix. It's not matrix A, but it looks like it's a square one. The numbers, the 1, 1 entry, the 2, 2 entry, the 3, 3 entry here, and so forth. Those are the elements that make up the main diagonal of a square matrix. The reason it's called main diagonal is not our problem. This won't come up in this course. Is these entries 1 unit off of the main diagonal are sometimes of interest as well, and not for us. Take a more advanced theory of matrices class. We got a graduate version of it at ETSU. And you'll talk more about some of these other off diagonal entries. But for us, we'll be interested only in the main diagonal if we take an interest in any kind of diagonals. A square matrix which has zeros off the main diagonal, it's called a diagonal matrix. We ain't going to be worried about this for a while. In chapter 5, we'll come back and talk more about diagonal matrices. But what that means is there's zeros above the main diagonal, zeros below the main diagonal, and for diagonal matrix, anything you like along the main diagonal. This is a particular example here. This example here is the identity matrix. It's the n by n diagonal matrix with all entries of 1 along the diagonal. So it's diagonal because these things are the only non-zero entries. The main diagonal entries are the only non-zero entries. And those main diagonal entries are all 1s. They could be something else other than 1, and it would still be a diagonal matrix, but it wouldn't be this matrix I'll denote with a calligraphy I, this identity matrix. Some more operations. Take matrix A to have entries A sub ij, matrix B to have entries B sub ij as usual. let those both be matrices of size n by n. So they're the same dimensions for both matrices. So this is different from matrix products. We'll define the sum, matrix A plus matrix B, to be the n by n matrix, same size as the ones we started with entries C sub ij, where C sub ij is A sub ij plus B sub ij. So to add two matrices of the same size together, just add corresponding entries together. So that's easy and reasonable. If we take R to be a scalar, then we'll define R times A to be a matrix with entries R times A sub j, just like you do with vectors. You take that scalar R and put it on or multiply it times each of the entries of that matrix A. This is my thing where I say it's not distribution. It might remind you of distribution. You want to think of it as distribution, you ought to be okay. Just don't tell me about it. So definition of scalar multiplication on a matrix setting, that's what it is. But you simply multiply all the entries by that scalar. So matrix addition, that works just like vector addition, except there's more entries. Scalar multiplication works just like it does with vectors as well. All right, let's look at another example. Number 6. Okay, they give us two matrices and ask us to do some scalar multiplication and some vector addition. Well, vector subtraction. Subtraction really isn't a legitimate mathematical operation, neither is division. There's only two operations, multiplication and addition, and this subtraction and division are related to inverses. So there's really no such thing as subtraction. Depends how we want to deal with this minus sign. We could treat it as a -2 coefficient, -2 scalar if you like. But the arithmetic is easy. 4a minus 2b, there's matrix A, there's matrix B, there's the 4 and the -2. Okay, we'll take this 4 and put it on each of those entries. Notice by conscious avoidance of the word distribute. Take, say, the -2 scalar, put it on each of the components, multiply each of the components by that -2. Do the arithmetic. So we've processed the scalar multiplication with the scalar 4 and the scalar -2. At this stage, those matrices are the same size. They can be added together. Component-wise, entry-wise, probably a better term in the matrix setting to distinguish it from the vector setting. Do the arithmetic and it simplifies down to this. The numbers don't mean anything in particular to us. How about the dimensions? Is it the right size? We're doing addition here. It should be the same size as the vectors, as the matrices we started with, 2 by 3, and it is. All right. Gee, I wouldn't be surprised if we didn't call this a linear combination of those two matrices at some point. Back to the notes. Okay, we transposed vectors in the last section or two. We transposed a row vector and got a column vector. We transposed a column vector and got a row vector. We could transpose matrices. Matrix B is the transpose of matrix A, denoted B equals A transpose, if B sub ij equals A sub ji. If a matrix A, say, equals its own transpose, then it's called a symmetric matrix. All right, so what you're doing is you're reversing the indices when you do this transpose procedure. Excuse me. So what you're doing when you reverse the indices is you're swapping rows for columns. Remember, B sub ij would be the entry in matrix B in row I and column J. So if we swap those indices, that's going to take that entry B from the ith row, jth column to the ith column, jth row. So it's going to do some swapping around. By the way, if I and j were the same and you swap I and j, as you do with a transpose, I don't change anything. The diagonal elements will stay right where they are. And the symmetry that you're getting from these matrices is symmetry with respect to the main diagonal. The entries above the main diagonal will be mirror images of the entries below the main diagonal. Okay, let's take that definition and work number 38 from this section. Where they say if A is a square matrix, then A plus A transpose is symmetric. All right. Symmetric means the matrix equals its own transpose. Okay. We'll let matrix A have entries A sub ij. Then A transpose, we'll just take the A sub ij entries, swap rows for columns. The transpose procedure interchanges the indices. So A sub ij becomes A sub ji. That's what transposing does. Notice it'll move dimensions around on these things as well. So if we want to take the sum, A plus A transpose, let's call that sum matrix C. Let the entries be C sub ij. So I want to talk about this being a symmetric matrix. Then we get matrix A plus matrix A transpose. That'd be A sub ij plus A sub ji. Add those corresponding entries together. That'll give us A sub ij plus A sub ji within a single matrix. So we've done the matrix addition there. So we get the C sub ij entry, ith row, jth column of this matrix sum to be A sub ij plus A sub ji. All right. To be symmetric is to equal the transpose, to have, in this case, C sub ij and C sub ji being the same. It's symmetry with respect to the main diagonal. So let's interchange the i's and j's in this little equation. All right, so we'll have C sub ji, C sub ji, A sub ij becomes A sub ji, and A sub ji becomes A sub ij. So we get C sub ji equals A sub ji plus A sub ij, which is the same thing we had over here, it's just written in a reverse order. But we're just adding real numbers together, that's commutative. So, hey, C sub ij and C sub ji, those are the same. That is, C equals its own transpose. That is, matrix C is symmetric. All right, so that went by pretty fast, so you might want to rethink through all of that. But we've introduced a new matrix C, checked it, and shown that it is symmetric by showing it equals its transpose. That's what symmetric is. We've shown matrix C equals matrix C transpose with this little relationship right here. Some properties of matrix algebra are the following. And the big observation in this is what's conspicuously absent. There is no distribution, there is no commutativity in multiplication of matrices. Oh, distribution, there's probably plenty of distribution. I'd expect us to have, we got two binary operations, right? We've got matrix multiplication and we got matrix addition. So I'll expect certainly the possibility for some differentiability. For some distribution. Okay, so we'll take three matrices, A, B, and C, such that the sums and products below are defined. That's their cheap way of saying, the dimensions are correct for the products that we're going to talk about to exist and for the sums we're going to talk about to exist. And let R and S be scalars. Then commutativity law of addition. Oh, sure, commutativity law of addition, matrix A plus matrix B equals matrix B plus matrix A. No surprises there, because adding matrices is easy. You just add their corresponding entries, and they're just real numbers, so the order doesn't matter there. So that doesn't surprise me, nor does an associativity law of addition. That doesn't surprise me in the least, because similarly of the way you add matrices. There's an additive identity. If we'll take, in this case, and I'm not too hot on this notation, we'll take 0 to represent the n by n matrix of all zeros. Yeah, it looks just like the 0 scalar, so I wish we had some notation to distinguish here. So I don't like that notation. But if we take the matrix of all zeros, add it to matrix A, or take A and add it to the matrix of all zeros. If we do this addition in either order, then we get out this equals matrix A. So 0 is the additive identity. That is the matrix of appropriate size of all zeros. So we have an additive identity. We have scalar distribution, R scalar times A plus B equals RA plus RB. So we get that kind of distribution. Shouldn't be terribly surprising when you think how we define scalar multiplication and how we define matrix addition. Matrix R, scalar R plus scalar S times matrix A. We get a distribution of that sort, which also shouldn't be a surprise, and you should be able to figure out how to prove these things with the addition stuff. Scalars interact when we have a product like this. If we take scalars R and S times matrix A, we could first take scalar S times matrix A and then take scalar R times matrix SA. Also, since there's only one matrix involved and the definition of scalar multiplication is pretty straightforward, that shouldn't be a surprise. Here we had some similar thing with dot products on this behavior of scalars. If I want to take scalar R times a matrix product AB, and start with the right-hand side here. If I want to take scalar R times matrix AB, I could take that scalar and put it on matrix B and then do the product, put it on matrix A and then do the product, or leave it outside and do the product first. Each of those will be equal. The book calls this scalars pull through, and I think this is very unique Fraley and Beauregard notation or terminology here, though the property's fairly universal. All right, and that's the first one of these that addresses matrix multiplication. Notice in each of these three, though, the A matrix is to the left of the B matrix each time. The scalar, it can bounce around. A and B have to stay A on the left and B on the right. Nowhere are we going to see commutativity. We get associativity for matrix multiplication. Claim is, if we take matrices B and C and multiply them and then multiply by A in this sense, that's the same as multiplying A by B and then multiplying by C. The order A, B, C has to stay the same on both sides, but we can multiply, we can associate B and C first and then multiply by A, or we can associate A and B first and then multiply by C. Usual associativity stuff. The identity matrix that we encountered times any matrix A equals A times the identity matrix on the other side. You have to state this on two sides because you don't necessarily know that we'll get the same thing on the left and the right. We do when we take identity matrices. And as they made the blanket statement somewhere above, this is very dependent on the dimensions being of the correct size so that the products exist. And we get a distribution law as follows. Matrix A times matrix B plus C is the same as matrix AB plus matrix AC. And similarly, if we had the addition on the left and on the left in the product instead of on the right in the product, so we're taking A times a sum, and here we're taking a sum times C. So they have to state these separately because we don't have that commutativity of multiplication. A plus B times C is AC plus BC, where those are matrices. So there shouldn't be anything surprising in this. I think the hardest one really to see is this one, and we'll go through proof of this one. I don't see that one immediately. Yeah, that's because of the funky way that we define matrix products, that row times column stuff, makes these that involve matrix products not entirely clear. These that involve matrix sums, these shouldn't be surprises. These, I don't see that, which is why we'll go through computation to demonstrate that. Okay, an example in the book gives one of these distribution laws. Let's go through and establish the associativity. That's also one of the exercises. So it's in these supplements. Let's do that. All right, as promised, this, I don't have an intuitive feel for this being the case, so let's prove it. Claim is A, B, and C are matrices with the appropriate dimensions so that these products exist. Then we get this associativity. A times B times C equals AB times C. Okay. Let the entries in matrix A be A sub ij. Suppose this is M by N. Then matrix B will have to be N by something. Let's call it S. Let matrix B have the obvious entries. Let matrix C have entry C sub ij. We're going to multiply B times C. B was N by S. So C will have to be S by something. Call this something T. So I got to introduce a bunch of different letters here on those dimensions. But A times B, they're the right size for that product to exist. B times C, they're the right size for that product to exist. Maybe practice a little bit here. How are we doing on this? What's the dimension of AB? That would be M by S. AB would be M by S. It's the outer dimensions there. Can we multiply that by matrix C as we need to? Yeah, the second dimension here is the same as the first dimension there, which I can describe as number of columns here equals number of rows here, which is what we needed for those dot product things to work out the way we use dot products to define matrix products. Okay, so tell you what, let's calculate this BC, or focus on BC first. The IJ entry of BC is IJ entry. We'd take B sub ik times C sub kj. That's exactly how we found the IJ entry in a matrix product. So we get the I as the first index on the first one, the J is the second index on the second one, and then we summed as these other two indices ran over the appropriate range. In this case, second index on B runs from 1 to S. In C, the first index runs from 1 to S, right? That's the dot product thing. So we'll take a sum from some dummy variable. Let's call it K. K equals 1 to S. And what we're doing here is in the ith row of matrix B, we're taking the first entry and multiplying it by the first entry in the jth column of C. Product of the second entries, product of the third entries, and so forth. So that's that row times column manipulation in terms of the matrix product. That's just the algebraic way to express it. Okay, so if we wish to find, say, the KJ entry of BC, then we'd have a similar type thing. So we're just permuting those indices around. Got my reasons because I want to take a, we got to do a second product up here. So if we have reasonable symbols, this isn't quite as nightmarish, but it takes some getting used to appreciate all this summation stuff. It's really just dot products. So let's change this from the IJ entry of BC. So I get that straight from the definition. Let's play around with those entries. Instead of having the IJ entry, let's talk about the KJ entry. So all I'm doing is changing indices here. I'm changing I to K. All right, so the I in this one will become a K down here. And I'm changing the dummy variable K to the dummy variable L. So the two K's have become L's and the I has become a K. All right. So that's simply rewriting what we just had that comes from the definition of matrix product with some different letters. I want to use different letters, and I worked at this a while to get this level of meaningfulness in it. So if we want to find the IJ entry of A times B times C, here you go. We'll take the IK entry of A and the KJ entry of B. So that's the reason I wanted to do this change. This matches with the definition of matrix products. I want to talk KJ because we use KJ entries in that second matrix in the definition. So I need the KJ entry of BC. Okay, it itself is a sum, and it's given by what we were just discussing. So we've got the IK entry of A times the KJ entry of B times C. Add them up. I need a dummy variable. We'll take it to be K. as we did in the definition. Sum, these, I can use distribution property. They're just real numbers. This is a sum of a sub k's on another sum. So I can use distribution. If you like, I can bring all the summations outside. But we've taken the a sub ik, distributed it inside. Let's see, we swap the order of summation. That's a commutativity thing there for real numbers. We're good. So we can write this as a sum from L equals 1 to S, sum from K equals 1 to N. Same summations, different order. A sub ik, B sub KL. All right, and here we've got K changing. If you look at this, C sub Lj doesn't have any K's in it. We factor it outside of this summation and get the C sub Lj over here. Now the L changes. We couldn't bring anything outside the sums on the left, but we can certainly do some factoring on the right. Okay, so we can factor and rewrite in this form that ij entry of A times B times C. Remember, we're trying to get out A, B, C. We're looking for something that would look like an ij entry of AB times C. That's why we've written it in this form. All right, so let's interchange, it says down here what we did, interchange the dummy variables L and K, dummy variables. We're summing over these, so it really doesn't matter what letter we use, trying to be somewhat consistent with the definition of matrix product. So we're going to interchange the L's and the K's from here to here. So we had an L on S outer sum, we'll change it to a K. We had second index of the B's was L, we'll change it to a K. First index on the C's was an L, we'll change it to a K. Now I look at the K's and change them to L's. We had a K here, change it to an L. We had K's here and here, change them to L's. And that takes care of everything. The I's and the J's were nowhere involved in the sums. Remember, we'll have a function of I and J. This is the ij entry of A times B times C. Now, if you look at this first summation, or this innermost summation, what we've got then is sum from L equals 1 to N, A sub IL, B sub LK. That is totally ith row of A dotted with kth column of matrix B. It's exactly what we had in the definition of A times B, the ij entry, sorry, the ik entry of matrix AB. So that summation, it's the ik entry of A times B. So what we've got is the ik entry of AB times the kj entry of matrix C, and we're summing over the k's. Trust me, peek back at the definition. That's exactly the ij entry of matrix AB times C. You've got entries of AB here. You've got entries of AB times C in this double summation. So we've got the ij entry of ABC to equal the ij entry of ABC. We've shown that the entries, when we take the product by multiplying by B and C first, is the same as the product multiplying A and B first, and then by C. That is, those matrices are the same. That's about as bad as it gets in terms of going through proofs involving the matrices. And what makes this one particularly hard is there's two matrix products to consider. Either B times C first and then A times that, or A times B first and then that times C. So there's two matrix products to consider, and that's why we got these double summations down here, and that's why I had to throw all those indices around. So my apologies, but that's as bad as it gets on this stuff. And it establishes something that I didn't think was very intuitive, namely associativity of matrix multiplication. Cool. So we've got pretty much everything but commutativity with matrix multiplication when it's defined and the dimensions are correct. We had claimed in part 9 of this theorem that the identity behaves in a certain way. Let's verify that. It's totally unsurprising. Take A to be, a matrix with whatever entries, let's just say 1 through 9. And let I be also a 3 by 3 matrix, but let it be the 3 by 3 identity matrix. Okay. Let's multiply I times A and A times I and make sure that we get A back out. Okay, so we want to take I times A. Matrix A was given to be this 1 through 9 thing. And the 3 by 3 identity matrix, 1's along the main diagonal, 0's off that diagonal. Let's do the arithmetic. You're going to like this because your best friends are there, just 0's and 1's. The more 0's, the merrier, by the way. All right, so we're going to do row times column stuff. All right, first row, first column. Be 1 times 1 plus some zeros. 1 times 1 plus some zeros. First row, second column, 1 times 2 plus some zeros. First row, third column, 1 times 3 plus some zeros. And similarly with the second and third rows. So we get all this stuff, but there's 2 zeros in these 3 pieces of the summation. That's 0, you keep the 1. That's 0, you keep the 4. That's 0, you keep the 7. You kept the 1, the 4, and the 7. Why, the 1, the 4, and the 7, that's the first column. Here's the intermediate arithmetic, and you see, not a coincidence, these little diagonal things going on here. Now they're separated by plus signs because I left all the zeros in. That's the reason they look like that. But sure enough, we get the same matrix A out when multiplying on the left by this 3 by 3 identity matrix. Let's do it on the other side. Let's take A times I. A times I, well, let's not get into it in great depth. It works on that side as well. You take A times I, you do first row, first column, picks off the 1 and loses the other stuff. First row, second column, it'll pick off the 2 in the second position and lose the other stuff because of the zeros. First row, third column, picks off the 3, you lose the other stuff. You get 1, 2, 3 in that first row. First, second, and third column, and similarly for the rest of it. So this should convince you that, yeah, the identity matrix behaves the way it should. And I like 0. Zeros really made all of this quite streamlined in the computations. Back to the notes. Properties of transpose. Okay, here's another one that's not immediately obvious. So I want to go through a little argument for that. Transpose was when you interchange the rows and the columns. So if I take a matrix, A, transpose it twice, first time, that'll interchange the rows and the columns. Second time, that'll change them back. So A transpose transpose equals matrix A. The sum A and B transposed is A transpose plus B transpose. That shouldn't come as a surprise to you. Addition of matrices is pretty straightforward. And this one, AB transpose equals B transpose A transpose. The order's different. I can, in my mind, visualize why that's the case. And you know why? It's because I can't really get a clean picture in my mind of what A times B is because it's that funny row times column stuff. Hey, B transpose A transpose, that's that funny row times column stuff too, except of transposes of these matrices. So let's go through and establish that one. And I feel obligated, at least in these videos, to give proofs of the ones that are not very intuitive. Okay, well, let's do this kind of the way we did with that symmetry thing upstairs, and a few more symbols. Let's let matrix C be the matrix AB transposed, and let the entries of matrix C be C sub ij. And the ij entry of AB, by definition, was exactly this. This is K ranging from 1 to N. We're running across the ith row of matrix A, and we're running down the jth column of matrix B. That's how you find the ij entry of AB. So we get this as the ij entry of AB. We've defined C, matrix C, as the transpose of that. So C sub ij is what we would get. Transpose means interchanging the indices. So C sub ij would be the ji, not ij, entry of matrix AB. So we'll have to swap the i's and the j's to get the c sub ij. That's the transposing. So c sub ij equals sum from 1 to n with a k parameter, a sub jk, b sub ki. Taken the i's and the j's and interchanged them. Algebraically, that's what transposing does. All right, so we found the ij entry of AB transpose. Let's find the ij entry of B transpose A transpose, show they're the same. That'll show that the entries are the same. And we've got to show really all of the entries are the same to show a matrix equality. That's why it becomes all this stuff with ij's. All right, let's look at matrix B transpose. That'd be B sub ij transpose. Let me introduce some new symbols. I think this is the easiest way to see it, and I'm not saying this is an easy way to see it, but there's a lot worse ways to interpret this stuff. Let's denote the ij entry of B transpose is a little b sub ij superscript t. So I'm treating that not as an exponent, just as a superscript. Of course, it's implying something about transpose. So let the matrix B transpose have entries B sub ij transpose, the ij entry of matrix B transpose. And you know, by taking the transpose of B, we get B sub ij transpose means interchange the indices, so we'll get B sub ji. I spent quite a bit of time on writing this one up to get it as clean as it is. I understand this is daunting stuff on first sight, but the ij entry of the transpose is B sub ji. That's all it means. Same thing with the A transpose. The ij entry of A transpose is A sub ji. All right, so if we want to take the ij entry of B transpose A transpose, we'll take a summation from 1 to k. We're doing our dot product thing. We'll run across first matrix is B transpose. So we'll go along the ith row of B transpose and down the jth column of the second matrix, A transpose. So having those little superscripts of T comes in handy here. This is exactly, by definition, how you would compute that dot product row dot column idea of how you would find the ij entry of this product, B transpose, A transpose. Well, let's convert that back into elements of A and B. Remember, we're trying to get the same thing we got before. B sub ik transpose, or B sub ik super T, I should read it, would be, let's see, related to the entries of matrix B by simply dropping the T and reversing the subscripts. So we'll drop the T and reverse the ik to get a ki, right? Same thing with the A's to get from A sub kj super T back to A's in themselves. We'll drop the T and reverse these subscripts. Drop the T, change the kj into a jk, and there you go. Let's write those in a different order. Let's write the A's first and the B's second. The pattern on matrix products has been the second index of the first one is the same as the first index of the second one. It's related to the row times column stuff. That's the case up here, right? Second index, first index. Second index, first index. All right, so we get something of this form here. And hey, that's the same thing we had before. That's the exact same thing we had up here. We had A sub jk, A sub jk, B sub ki, B sub ki. And we saw that that equals C sub ij, the ij entry of AB transpose. So the ij entry of this, given here, is the same as the ij entry of this, given here. They got the same entries. They're the same matrices. So there's how transposes interact with matrix products. It's weird. The order got swapped around, but there's why. We have associativity of matrix multiplication. We're going to need that. But we went through proof of that. So I consider these things largely water under the bridge. Now we can use them. Transposing, we'll do a bit of. Matrix products, we'll do a lot of that stuff. We'll do a lot of matrix multiplication, and associativity there will be essential. So that takes care of our introduction to matrices and their algebra. What we'll do in the next section is introduce a a brand new concept, systems of equations, systems of linear equations, and some new manipulations with matrices, and then we're going to spend a bunch of time with matrices for the next several sections. Matrices will play a role throughout the rest of the course. Even though we may be having conversations about vectors, we're going to use matrices to have those conversations. I can't wait. I'll see you there. Have a nice day.